we started using them when my company, the company I work for, turned from small startup into something bigger, and we had more servers, more clients, and we needed some real metrics dashboarding system, and we needed to monitor our applications all the time. And one of my colleagues came back from a company conference, which name starts from G, and he said they showed there a great tool. It's called Graphite, and we can dashboard everything using this tool, and there are some libraries that will allow us to instrument our applications. And we started using something what was called Metrics.io. It was our Codahalemetrics. Now I believe it's maintained by DropWizard, so it's DropWizard metrics. And although I will be mostly speaking, saying Graphite, metrics, the same problems are encountered with other tools, and authors of other tools also need to solve the same problems, and they probably choose the similar way. So if you're using a little different stack, probably underlying models are the same. You should look into it, and probably there will be the same problems, and this talk will still apply. When we started investigating the problems with these tools, when we got reports from clients, occasional reports saying that something was slow, something wasn't working. Well, we looked at our dashboard and said, well, that's a lie, because it clearly says that it's fast and it's working. And then we started looking into raw data, the raw response data in our logs, and it turned out that our logs say a different story, that the dashboards show completely different things than that actually what is the real performance of our application. We started digging into these libraries, and it turns out they just lied to us. They use invalid statistical models, they drop some data, and they don't report everything, and on top of that, Graphite also loses some data. So we found ourselves that actually we were doing the same thing most of other people does, the same best practices, and we came up with something that is completely unreliable. So we felt like we were doing, instead of science or real thing, we were just doing cargo cult, and there was nothing in it. Do you know the term cargo cult? Yeah, so quick introduction that cargo cult term was first used. Okay, it was first used by Richard Feynman, and it started when US troops during World War II set up a bases on islands of Pacific. And there they set up landing strips, control towers. There were these guys with noise cancelling big headphones, waving hands, showing planes how to land. And the planes land, and they brought cargo, which was nice. It was medical supplies, food, weapons. So when they left from those islands, people that originally inhabited them also wanted this stuff. So they started building control towers out of wood, planes out of wood. I've seen a picture of someone standing on a fake landing strip with headphones made out of coconuts. And he was waving hands, trying to summon the planes down, but the planes didn't come. So I sometimes feel like that. They were doing, in theory, everything right, but there was lacking a substance. There was something that wasn't there that made all this real. So I feel like that. I fall for this, well, if I try to profile some part of application without verifying that it is really a problem, I change the code, deploy to production, and nothing changes. It's still slow, right? So I feel like this guy waiting for a plane. I don't know if you do the same, or I'm the only idiot here. Okay. So what Richard Feynman was saying, that we might laugh at these guys. This is other part of his talk when he also was talking about Middle Ages and the other superstitions. We might laugh at these guys, but actually we are doing the same right now. We are not verifying our hypothesis. We are not verifying our results, and we are going just with it. So that's the origin of the problem. And if you were at the keynote presentation, which I think was very good, Hadi said about chasing the silver bullet. There's also other part to this. When we are chasing silver bullet, it implies that we are looking for a solution to some problems. But actually, in IT, we are a fashion industry. We just want to get a new shiny thing and try it out without any purpose. And if we drop all these new methodologies, new tools, there is only a few things left that won't change ever. And these are some basic engineering principles that if we follow, I hope will probably help us through survive any new framework, any new tool. If we apply some basic reasoning, science, and just common sense. So if I told you that it's not that easy to measure this, so maybe why bother? Maybe there's no point in doing that. Well, the basic rule is that you get what you measure. If you work at a corporation, you might be, especially big corporation, you might know this phrase because it looks like that. There's a VP. You know, the job of VP is to have ideas, whatever they are. His job is to have ideas, and he said, for example, he has an idea that we need to measure code coverage, and it should be high, right? So he will get the high code coverage. It doesn't say that there are assertions in those tests, right? That there are less bugs. He wanted to measure code coverage, and that's what he got. So it's the same with any other measurements. We get what we measure. If we measure it incorrectly, we optimize wrong stuff, we complicate the code, and it just adds to the complexity of the code without any results. So if we want really to measure, then we must think about how to apply this, and what is our SLA and what is our user base. You might be creating different kinds of applications. I will be mostly talking about the one that, well, there are infinite number of users potentially that come and query your web service or query your application. But this might be not only web service, maybe some desktop application that connects to some backend servers. And to show you the scale of the problem, there is a survey. It's 1 year old. It says that out of 3,000 biggest websites, on average, we have 112 objects to download per website. This means that when your user hits your website, it potentially have 100 calls to do. Of course, we optimize it. It's not one object per call. Static content is on CDN probably, but there is probably a few calls to your backend services to generate dynamic data, the data user wants. So if it's only a few calls or maybe one call, think about this. If there are several calls in your backend to gather this data. If you're working in a hipster company, you probably have dozens of microservices there. And all this adds to latency, and all this adds to the way and complexity of measuring it. And what's more, during a session, user will refresh your page, or maybe he will need to go into some sub-page, so he will request many pages. Our product is web analytics. So our users will sometimes sit all day and refresh the pages. And before before we developed the product, I heard that users were basically they were deploying it on their own servers. They're paying license for something that connected to MySQL. They put millions of data in it, of visits, of advertisements there. And when they wanted to query it, it took hours sometimes. Right now we do it in seconds. And if it's we have a glitch or we have a problem and it takes 1 minute, then some of them will write us email that we suck. And we should actually, he said that one of the users said he will go back to his old stack. So the conclusion is that users want more and want it faster. And there is hard data on that. Amazon did a survey saying it's about the Amazon.com. It's not web services, it's their e-commerce site, saying that every 100 milliseconds of slowdown of displaying their page makes them lose 1% of their clients. So think about the magnitude Amazon operates, and 100 milliseconds means they will lose millions. Google did similar survey, but they didn't get as harsh results as this. But what's interesting is that they, on purpose, injected failure into their systems. So as they created slowdowns for some users, and they observed what those users do. That's very ethical, right? And it turns out, but the results are very informative, at least for us. So the users, when they see slowdowns, they operate the web page, and if it's slower, then they go away, change to some competitor. But the problem is that if it was slower, they will lose interest in your page for some time. The slower it was, the longer it will take for the user to come back ever to your web page. So that's, I hope I have convinced you to do actual proper measuring of those latencies. And as I say, I will be talking mostly about Graphite and the metrics in Java, but there are other tools that are similar. I guess I wanted to ask you to tell me what kinds of tools you use, at least which one of you do dashboards? Okay, so not that many. I guess the rest of you doesn't need to, or maybe I will convince you to that you should. Which one of you use Graphite as a backend at least? Okay, I see 2 people. Okay, yes, that's the stack we use. So the front end is one thing, the backend that gathers the data is from Graphite, right? Yes. Okay, and are you instrumenting Java? Okay, great. Okay, thank you. So stand back, we try some science now. This is except from Graphite, but this shows what kind of metrics on the Java side are sent to Graphite. Of course, these metrics are the same that any other tool would send. We have mean, which is just a fancy word for average. We have max. We have minimal response time. Really, I will buy a beer for a person who will tell me what's the point of that metric. Minimum response time. Well, yeah, but what does it give you?
What do you mean? It gives you the way to convince your boss that you are awesome.
Yeah, you're right, but that's the job of average, and I'll be talking about it later. Then we have percentiles. Percentiles, just to refresh your memory, if you have like 30 percentiles, it means that this number, 30 percentiles, it means that half of the samples, less than half or half of the samples are below this value or equal. So this for P50 it's half, and of course for others it's 99%, for example. So first, let's take mean. Why not to measure mean? It doesn't make sense. It's really a pretty random number, and it looks nice on it looks like nice on the dashboards. This is Grafana dashboards. It shows mean response time from many servers. And the problem is that it usually looks good and it doesn't have anything to do with reality unless something like this happens. There's a latency spike here, right? We need to investigate it. It's strange. But actually, nothing happened here. When we looked at logs, it turned out that these numbers are a little, these are not the exact numbers we had with logs, but they're close enough. Usually we have 100 queries per minute. That lasts about 150 milliseconds. And there was one user who was constantly, probably he set up a bot, requesting a large amount of data. It was about every minute. So when we had so many queries per minute, we didn't see this one query, and on average it was fast. But then it was during a weekend. At one minute there were no other users, almost no other users, so we saw this latency spike. Actually, it was every minute. So this is the, usually average is very good, it's better than your system works, but sometimes it can play tricks on you. And if that's not enough to convince you that it's not really a good idea, then there is this set of data. It's called Anscombe's quartet. Anscombe was a statistician from Britain who evangelized using graphs or graphing statistical data as real mean to investigating actual data sets. And he created these 4 data sets that have exactly the same mean, median, and variance. If we looked at these 3 properties of those data sets, we would think that they are the same. But actually, when graphing them, they're completely different. So my conclusion is that plotting mean is for showing off to management. You will show nice numbers. So it's like minimum, but when you tell your management that it's minimum, then they won't believe you that it's actually a good metric. But with mean, maybe they will. So right now I was talking how we can actually, usually we lie to ourselves, and we will continue this. This is how to lie to the management. Of course, I'm telling you this so that you don't do this, right? It's immoral, right? So you can always do it the dog bear way. So you can set up a dashboard so that the management will do more decisions while ignoring it. And it doesn't matter if actually the statistics are real. So let's go a little up with the accuracy. Let's use median. So it's 50 percentile, right? How do we compute it? It's the middle element of set of measurements. So if we have a measurement, we need to sort it, and we select a middle element. In this example, there is no middle element, so we just take average of the 2 elements. What's interesting here is, apart from the case when we average 2 elements, the median is 1 element from the set. So it will not be arbitrary random number computed from the set. It will be one that actually happened. So that's better. But what's worse is that it's very stable. If you ask a statistician, it's very nice, actually, for the median to be stable, because he would say, if you measure something and some of your samples are bad, you know that they are tainted, then for median to change, you need to have more than 50% of bad samples. But for us, it's completely useless property, because, see, we can have, instead of 23 and 42, we can have some great latency spikes, and median stays the same. So it's also good to show to management. Well, taking into account what I said about how many requests we send to the service and how many times user interact with your application. Let's say that we want to graph percentiles. Take the 50 percentiles as an example. Let's say, okay, we want to graph it, and we want it to be low. And if we optimize our application so that 50 percentile is low, we must ask ourselves how many times the user actually experience it. So we say that our application, according to this metric, is fast. User sends a request, and what is the probability that he will see this number? Well, we calculate it like that, and n is the number of interactions. If the median is latency of your 1 microservices, then you must use number of microservices here times the interactions of your clients and span it whole day. So actually, what is the probability that he will see this? If he does only one call and there's one service, that's obviously 50%. But if there are like 5 services involved and your client does 2 calls, then it's 0. Actually, there's no probability that he will see this good number, which is the median. So we should go up. Let's try 99 percentile. I showed this slide to a colleague one time, and he said, wow, 99, it's a very big number, it's a very harsh requirement. Well, if you're doing microservices, then probably your microservices serve like tens of thousands requests per second, because what's the other point of having small functionality in server if you need to launch hundreds of them, right? You probably have one instance of microservices that does a lot of calls. And 1000 is very modest number. And in that case, the latency that is worse than 99 percentiles, of course, happens 10 times a second. So you must ask yourself if 99 is high enough. Maybe we should use 99.99. So just for the record, this is the probability. If we, after about 70 interactions, so your user times the number of services times the number pages he refreshes, about here, there's 50% chance that he will see the number worse than 99%. There is also other problem with average, with percentiles. There are absolutely no mathematical operations that you can execute on percentiles. If you have percentiles from different servers or from the same server but different time moments, then there are no operations that you can apply to them and you will get data that makes sense. This example, I made it up, but it illustrates how wrong it is. If we have 2 servers, one server is getting small load, so it's fast. The other server gets a lot of load, so it's much slower. If we get a percentile of response times from both servers and average it, we get the random number. So if you want to develop random number generator, then you can average percentiles. Apart from that, it doesn't make sense. And if you have a small troll inside you, we all have, you can look at dashboards, for example, on a Grafana website or some other stuff. Actually, I'm not sure that the Grafana has still those dashboards there, but a lot of people do averages, for example, average percentile across the whole cluster, or average percentile across time spans. And of course, if you know how Graphite works, Graphite basically, it needs to aggregate data. If the data gets older, or you want to display a time span that does not match exactly pixel per pixel to the number of minutes you have, then it needs to do some mathematical operations there. Usually it's average. You can change that, but you can do max or anything else. It will skew this, and you will lose important data here. So we can take advice from the king of hearts, from Wonderland, which he says that if there's no meaning in it, then we shouldn't look at it. So that's even better. And there's one more thing. There's maximum. We plot maximum. It's nice. It shows you the worst cases. Sometimes you can't see anything on that dashboard if the worst case is very long, and so every other case is not shown on the graph, right? It's very small pixels, but it shows us the real performance of application. And with the max, it's the same problem. We cannot do anything, any mathematical operations there apart from maybe taking max. So if we have a feed of servers, when we take maximum of maximums, then actually that's a real number and it makes sense. And if you average maximums, then every time you average maximum, a new JavaScript framework starts. So that's your fault if you do this. Okay, so there's a small demo time. This is how we lie to ourselves. I will show you how the metrics lie to us. It will be hard while holding the microphone. Basic class used by CodaHale metrics is timer. Its usage is very simple, like you might think. We have a timer, we record, we update it with a measurement. Let's say it contains all the data in nanoseconds. So unless you're doing high frequency trading, it doesn't make sense to have such a fine granularity. We're mostly measuring it in milliseconds. Can you see this? I can turn into presentation mode. Yes? Okay, so let's try it that way. Usually we just update the timer and nothing else. We don't care about reading from a timer because that's the job of the component that sets the data to Graphite or somewhere. But here we can try to get the data to just show how it works. And for example, we can plot max here. Okay, so we can see that we displayed that the maximum for this timer right now is that many nanoseconds. Maybe this will be better. Okay, it's 1 millisecond. Let's simulate our application that we'll be measuring. Let's say we have 1,000 requests, and we get the extract the data every 60 seconds. Let's say we'll be randomly logging that latency. And by the way, that's just for demo. Don't extract thread local random into a variable and pass it anywhere because it will break your applications. Never. Only on demo. Okay. Thanks. It's so easy when you sit there, right? Okay, it shows 0. Nice. So the maximum is 0. Can you believe that?
That's because you are casting the random too low.
Yes. Thanks. Believe it or not, I wrote this code like 10 times before this presentation. Okay, it's 999. So it makes sense, right? The maximum that can be here is 999. So maybe that makes sense. Let's simulate a real application. So we'll be having some pauses. GC pauses, maybe pauses from some Linux scheduling problems, similar stuff. Okay, so let's, with probability of 1%, let's inject some kind of pause here. Like 20 seconds. And see what is the result here. Okay, it's like 19 seconds. So I will show you a working example. Here is more pauses injected. So we have a timer here, and we inject pauses with some probability of 5 seconds, 20 seconds, 2 minutes, and so on, and see the results. Actually, we're only interested in maximum from the timer. And here, we additionally calculate our own maximum. So it's very easy, right? We take maximum from every latency we measure. And now the fun starts. This is real maximum. This is, of course, it's in milliseconds and not seconds. And it was right this time. That way it was. Okay, so there are some technical difficulties here. Yeah. Thanks. Okay, so this is the maximum that the timer measures, and this is the maximum that we will measure here. Okay, I hope this time it works right. Okay, so what is the result? The real maximum is in milliseconds. So we were injecting pauses of up to 2 minutes, and actually we were able to inject pause of 117 seconds here. And the timer from the metrics library show us that there was a pause of 19.5 seconds. We can do it all day long, and it will be sometimes better, sometimes it will be up to 2 orders of magnitude of compared to real numbers. Okay, so it didn't went smooth, but we see the results that actually the timer sucks and it will not display anything that is remotely real. And I have graphed such an experiment so that I don't have to be humiliated here by not being able to do it. And the green line shows the real spikes of the application, and the blue line shows what Graphite and the matrix library show us. So it shows some milliseconds here, and actually 2 times it found the real problem, and this is what we have seen, the blue line. And the green line is what the client see. There's other problem with this. The blue line here is the Graphite, and the green line is the real maximum. So this time, when we have very small number of requests, when there is a maximum injected into a timer, it will last forever sometimes. So it takes a long time before the maximum goes down. Our service is back up, it's running, and on the graphs we see that it still has the maximum here, and there's still something going on. But actually, it's already down. It's already working. Okay, what's the problem with this? It's the problem with the statistical assumptions behind the timer. So we see that inside the timer there is something called reservoir, and it's the data storage. And what's the problem with this data storage is that it's exponentially decaying. So it doesn't hold the real data. It has only a statistical representation of it, and it decays with time. So it removes the old data, adding new data, but at random. So it stores 128 random samples. Think about it. We just put 60,000 requests there, and it had only 128 slots. So it needs to decide what to drop out. And in order to do it, it needs some kind of statistical model about our requests, and it says that it assumes normal distributions. And all the tools that drop such data do this. Every time you would see that it says assuming normal distribution, and you should be suspicious of such tools. You should, in computer science, the normal distribution never happens. So when you see a tool that says that, you know that the data will not be accurate. The normal distribution is a very nice thing, and some of the people, statisticians like it very much. Here is the equation, and it's defined by only 2 parameters. So if you know those parameters, you can compute anything about this distribution. So for example, if we want to know 95th percentile of your response time, if your response times are distributed normally, you only need those 2 numbers, and you can calculate arbitrary results from this, and they will be correct. But in real life, there's nothing in IT that behaves like the normal distribution. Maybe the height of your users, but nothing else. Let's see it here. This is a histogram of response time. So we have buckets saying, okay, this is how many requests compute in 0 milliseconds, 1, 2, and so on. This is the number of requests. Does that look like a normal distribution? Or maybe a little. Well, it doesn't, but you can. On purpose, I created this so that it may resemble the normal distribution. But if you add GC poses here, when you add old generation GC poses, when you add poses from calling database, which has its own distribution, and other stuff that happens on your server, this completely doesn't look like a normal distribution. This is a multimodal distribution, and standard statistical tools does not have means to approximate it. So that's why all the timers and all other tools that would assume normal distribution are lying to you. And that's, they will be dropping all the outliers from this. And there's one other problem with the timer. because it's exponentially decaying and is driven by updates. This is an example of a service. The blue line is the response times. And we graph the blue line, it looks like this. It doesn't look nice, right? Because it's jobbed and it's not smooth, so there's something strange here. At some point, our service was ideally replying every time with the same amount of time. So there was something different and strange. Well, it was down, and we didn't make any calls. The service was down. This green line represents the number of requests. It turns out when the timer is not updated, it will report the same time every time you ask it. So if you're using it, then if you see something that doesn't look like real-life statistics, probably maybe your service is down. That does it. And if you're concerned about this, just there's a blog post by some company that tried to solve it. There are some solutions to this. So all these metrics lie to us, and there's no. Is there any hope about this? Well, I will try to show you a few tools that we have with that. And one tool is HdrHistogram. This class is something similar to the reservoir in timer. So this is a bucket that you put data in, and it tries to accurately show you the results. And what it does is, well, it can contain all the data that you put there, right? That's the one solution. You have like thousands of requests. You have many timers. When you put this data there, you can try to hold on to the real data, raw data, but it will consume a lot of money, of memory, right? And it's not efficient. That's why people try to approximate it. And this one, it doesn't assume any distribution. It just works a little like floating point number. If you have small numbers, then they are very accurate. The larger the number are, they are less accurate. So you can configure it saying, okay, I want to measure seconds or minutes of response times, and I want it to measure with accuracy of 3 decimal places. So it will be like, if you log 10 milliseconds of response time, then it's important if it's 9, 10, or 11. But if you log 120,000 of milliseconds of response time, it doesn't matter if it's off by 2 or 3 milliseconds. So it uses this to dynamically scale. That's why it's called high dynamic range histogram. And what's better, it has so accurate data model that actually when you capture it from different servers, when you capture it from different time ranges, you can make operation on those histograms. So you can add them, you can add 2 histograms and get the real accurate data out of it. On top of this is a recorder class. It's a very interesting class for someone who likes concurrent programming, because HdrHistogram is designed for very demanding applications. It doesn't create any objects who are operating. It is very fast, and it is not thread safe. If you want it to be thread safe, well, there's the recorder class will do that. It will use a concurrent version of it, and it will do something like double buffering. So you, all the writers will write to one histogram, and it will work. It's not only log-free, but also wait-free for the writers. And when someone wants to read it, he will swap, the thread will swap atomically the 2 histograms. So writers will write to the other one, and you can read data that is stable. And then you can swap it again every time you want to read it. There are some other solutions. And if you have, actually you're using these metrics, you can go and try to use other reservoirs, but all they do is capture all the data that is coming to them. So they will use much more memory. There are some performance metric I tried to do, and here we can see that we can do about 7 or 8 updates to HdrHistogram each microsecond, and all other metrics are slower, apart from this one reservoir who just has an array of long, and you put every measurement is inserted into this array, and if you go over array, it will overwrite old ones. That's also a valid approach if you scale it correctly. There's one more thing to talk about it. Benchmarking. Well, the benchmarking right now is the most important and leading cause of statistics in the world. If you look at benchmarks from some vendors about NoSQL databases, our database is fast, Cassandra is fast, our Spike is 10 times faster, as I claim, and most such benchmarks are flawed. And this is very simple thing. If you try to measure the response times of your applications from the load driver side, so we are setting up something like JMeter, and we are sending requests to our database or our application. And what happens is called coordinated omission. Coordinated omission is the effect that you're losing some of the samples. So that's why omission. In general, is not bad. If you lose a random number of samples, then your measurements are still valid. You might lose some outliers, but in general, if it's random, the data makes sense. But coordinated omission means that you coordinate with some effect, with something which, for example, might slow down your application, and you lose data only then. So it was formulated by Jill Tene. He's selling a JVM that is, well, probably is as fast as Oracle JVM, but it shines and is much faster in the high percentile. So where the JVM is very much stressed out, Oracle would fail and the JVM will prevail, and they have this garbage collection algorithm that will still work. And he tried to show people, he said that he tried to show people that it's worth buying this stuff, but without proper measurement, he was unable to show actually that in this small amount of requests, actually it matters, because most measurement techniques would drop just this data. It happens when, let's see, this is time and the application runs. This is the time that we see measured on the response times. And here we have a 4-second pause. If we set up JMeter or other load driver to send requests to our service, let's say 100 times a second, and there is a 4-second pause. So the JMeter will send a request that will be reported at 4 seconds. So probably it will report the maximum that it was 4 seconds. And it will wait for the response, right? After 4 seconds, it gets the response, and it will go happily sending another request. But what about the requests that should have been sent in the meantime? There are 399 requests that are missing, and no one care about them. In real life, users would still try to kill your service. There would be requests coming here while the application is stopped. And JMeter actually, it's like it's plotted with your application that when it stops, it will back off, say, okay, I'm not sending more requests. And I have a demo here. I hacked the JMeter to display the old statistics and the new version of statistics. So we try to run JMeter and see how it behaves in such scenario. Okay, I will move it when I start the application. One moment. Okay, I started the application that just replies to the request. And we measure how it behaves. Okay, I'm starting JMeter. It should show somewhere here. Okay. In the moment, I will try to use a loop to show you the exact numbers. But right now, let's open a sampler And what we do here, we just send HTTP requests 100 times a second. So this is the how many times a minute we will be sending them. And we can see here, okay, we have a throughput of almost 100 requests a second. There are 0 numbers of errors, and we can see here the number for maximum and other stuff. And here is the hacked one. So right now application is not stopping, actually. I'm not introducing any latencies. And already we can see that the numbers are different. There are some requests that are missing, and normally JMeter would say that it's like 3 or 2 milliseconds here, but really it's higher. But let's try to introduce some pauses. Okay. This is the server. I want to pause. Okay, I'm sending stop signal here. So it's stopped. Let's try with JMeter. JMeter stopped. There is nothing happening here. So the thread is waiting. And let's start the application. Okay, can you see that? So the 90 percentile is what? It's 1 millisecond or 11 seconds. In standard operation, JMeter, as well as a lot of other benchmarks, we just drop the request. This second line counted all the missing requests and added it. So there were actual users who didn't get the response here. So if you're doing performance testing and you want to launch your application to production, saying your client, okay, we know that it will work 10,000 times fine, and there will be only one outlier, then probably your data is much too optimistic if you use this approach. So this is a graph of such a test. Here we can see that standard approach would say, okay, we have over 90 milliseconds, one time in 100,000. And actually it's only it's about one time in 2,000 or 3,000. So we are almost 2 orders of magnitude off. So what we can do about it? Well, we can ignore it. It's always the good choice, and especially if we have a batch system, then we don't care. The other way is mathematically correct. It's easy, right? We send a request, and we know when we get the response, we know how many requests we missed, because we know we should send every request every 10 milliseconds, and we waited 4 seconds. So it's easy to calculate all the missing requests and add it mathematically. That's what I did, and the histogram supports it. The other way is to correct it on load driver side. So when we send a request, we should have a time, find out time at which this request should be sent. If we are over that time, we are late sending this request, we should add it to request latency. But for some systems, all this is unacceptable. And there are systems when we have such a pause, we just fail the test. Because if there's such a pause, it means that people die. So at that point, there's nothing to correct, right? There's also one problem with this mathematical approach. If we have a server that is down because there's too much load on it, when it gets up, okay, it replies, we correct mathematically all the missing responses. But when the server gets up, it has only one request waiting in a queue, right? There should be hundreds of them. So probably in real life, it would never recover, because every time it gets up, it would have hundreds of requests queued, and probably would get down again. So the solution to this is basically use many threads, use asynchronous testing, asynchronous clients, and use many servers. For example, Twitter IAGO was designed to simulate real users in a way that it will start a main server that will produce the request, and it will dispatch those requests to many servers that are actual simulated clients. So if there is even coordinated omission, there will be many servers that actually will see this problem. And one of our testers used it, and he adjusted it to Amazon auto-scaling groups. So if there is not enough clients, there's servers that simulate clients, the Amazon will automatically add more. So this is quite a nice solution. The downside is that it's in Scala. So that's it. That's the motto of the JMeter. And as a summary, remember after this presentation that we should measure what is meaningful. We should set up SLAs. We shouldn't trust not only timer class, but all the tools that assume normal distribution. Do not average percentiles or maxes. Thank you. That's it. There are some sources and yeah. Okay. Okay, so here are the sources of the pictures or stuff or the guys and web pages that I took additional data. That was, well, it's not only we've seen that problems. There are people who researched it very deeply, and I have took from their writings. And if you're interested in queuing theory, in measuring stuff and planning capacity, there is a very interesting book. It's quite demanding, but it's the best, quite academical script I've seen in years. So that's it. Thank you.